Today we're going to talk about combinations. Now remember last time we talked about permutations? Combinations is similar with one difference. So a combination of R elements from a set of N elements is a selection of the R elements without regard to order. Now notice how that's very similar to permutations, but the only difference is here that order doesn't matter. Now here's the formula. So say you have N elements and you are taking R elements at a time. Then on the left here, we would read this N, choose R. And then on the right, we have N factorial all over N minus R factorial, R factorial. Really what you're doing here is you are finding the number of permutations, and then there are some permutations consisting of the same objects. And so we're going to divide those repeats out, and that will give us the number of combinations. Take a look at example 1. How many committees of 3 people can be formed from a group of 8 people? Now notice how this is different from a permutation problem. If you're coming up with a committee of people, and say there are no roles for each of those committee members, then they're simply on the committee. If you choose 3 people, it doesn't matter the order in which you choose them. No matter how you chose them, in what order you chose them, it's still the same 3 people that are on the committee. So in this case, we are finding 8 choose 3. So that's 8 factorial over 8 minus 3 factorial, 3 factorial. So this is 8 factorial, and then on the bottom we have 5 factorial, 3 factorial. Now remember what factorial means. This 5 factorial and 3 factorial cannot be added together. You're multiplying them. So I would write this all out. So we have 8 times 7 all the way down to 1. And then 5 factorial, so 5 times 4 times 3 times 2 times 1, and 3 factorial, 3 times 2 times 1. Now we want to see if we can cancel as much as we can out. So we see we have the 5, 4, 3, 2, 1 up on top, and we have that on the bottom as well. That leaves me with 8 times 7 times 6 on top, divided by 3 times 2 times 1. You can also see that the 6 on top cancels out with the 3 times 2 on the bottom, so that leaves you with 56. So there are 56 different ways of choosing 3 people from a group of 8 people to be on a committee. Now on your graphing calculators, there is a way to find 8 choose 3 without having to do this all out. So on the graphing calculator, you would press the math button and then go down to probability, prob for probability, and then you're going to find the function that says NCR. Now depending on the version of your calculator, sometimes if you have one of the older versions, you would have to, before you get to this function, you would have to put 8 in, then find the function, and then put 3 in. On some of the newer calculators, if you go to Math Probability NCR, it'll show up with a C with 2 blanks in there for you to fill in, and you can fill that in. So on the older calculators, you'll have to do 8, then find the function, and then put 3, and then hit enter. Alright, example 2. 3 lawyers are to be selected from a group of 30 to work on a special project. In how many different ways can the lawyers be selected? Alright, so we have a group of 30 lawyers, and we're only choosing 3 of them. It doesn't matter what the order is, it's still the same 3 lawyers working on the project. So this is going to be 30, choose 3. So that's, I'm not going to write this completely out. This is 30 times 29 all the way down to 1. And then on the bottom we have 30 minus 3, so that's 27 factorial, and 3 factorial. Now you'll notice that the 27 factorial is going to cancel, and that will help you simplify this to 4060. Alright, and how many ways can the group of 3 be selected if a certain lawyer must work on the project? Okay, so out of those 30 lawyers, if one of them has to be on the project, well then there are only 2 more that we need to choose from, and only 29 to choose from. So, since now we're only choosing from 29 lawyers, and we are only choosing 2 of them, that would be 29 choose 2. Okay, simplifying this, we have 29 times 28 times 27 factorial. On the bottom, 27 factorial 2 factorial. And that is going to be 29 times 28 divided by 2 factorial, and so that's 406. Example 3. A salesman has 10 accounts in a certain city. In how many ways can he select 3 accounts to call on? So there's the salesman, and there are 10 accounts in the city, and you want to figure out, well, if he can only see 3 of them, how many different ways can he come up with 3 accounts to call on? All right, so there are 10 altogether, and we're choosing only 3. It doesn't matter the order in which they're chosen. So 10 choose 3. So that's 10 times 9 times 8, all the way down to 1. And then on the bottom, we have 10 minus 3, which is 7 factorial times 3 factorial. 7 factorials will cancel, leaving us with 120. So 120 ways for him to select 3 accounts to call on. In how many ways can he select at least 8 of the 10 accounts to use in preparing a report? Now this one's a little bit trickier. This is how many ways can he select not just 8, but at least 8 of the 10 accounts. That means he could select 8, he could select 9, or he could select 10. So what we're going to do is we're going to find out how many ways there are for him to select 8, how many for him to select 9, and how many ways for him to select 10. Once we've found the number of ways for 8, 9, and 10, then we'll add all of those together, and that will give us the total number of ways he can select at least 8 of the 10 accounts. So let's start with 8. So that would be 10 choose 8. We'll go ahead and apply the formula to it. And this ends up being 45. Now we'll go up to 9. So if he were to select 9 of them, how many ways are there? 10 choose 9. And that comes out to be 10. And then lastly, 10 choose 10. How many ways are there for him to select 10 out of the 10? Well, you may have already imagined there's only one way for him to choose all 10 of the 10 accounts. And so the math does in fact match up with that. So now we want to come up with the total number of ways. So now we will add the number of ways to choose 8, the number of ways to choose 9, and the number of ways to choose 10 all together. So 45 plus 10 plus 1, which is equal to 56. So altogether, there are 56 ways that he can select at least 8 of the 10 accounts in preparing the report. Okay, so we've done a lot with combinations, so let's just compare combinations with permutations, which we did last time. So permutations versus combinations. So permutations are different orderings or arrangements of R objects are different permutations. Combinations, on the other hand, this is where each choice or subset of R objects gives one combination. Order within the group of objects does not matter. And then we have the formulas for each, so you can compare the two, the only difference being that n choose R has an additional R factorial in the denominator. And that's really just taking out all the different arrangements of those objects, all the different orderings of those objects, so that you only get the combinations. Now in terms of clue words or phrases, these are not the only ones, but these can be helpful if you're trying to determine if it's a permutation or a combination. So with a permutation, clue words that you'll see are arrangement, a schedule, an order. Other things might be how many ways are there of choosing first, second, and third place. How many ways are there of coming up with, say, something with different roles? So if it's not just coming up with a group of 3 people, let's say how many ways are there of having a president, a secretary, and a vice president? So those would also be clues that you're working with a permutation. For combinations, clue words could be like a group. How many ways are there of choosing a group of students? How many ways are there of forming a committee of 5 people? A set. So how many ways can you come up with a set of books? How many ways are there of coming up with a sample of boxes. All right, so in the end, order matters for permutations and order does not matter for combinations. Really, that's the one thing you're trying to determine when you're looking at a situation and trying to figure out if you're looking for a permutation or a combination. So in this next example, we're going to determine in each of these scenarios not what the answer is, but whether it's going to be a permutation or a combination that we're trying to find. So the first one, how many 4-digit code numbers are possible if no digits are repeated? All right, so typically with 4-digit code numbers, there is an order to them, and so we would say this is a permutation. A sample of 3 light bulbs is randomly selected from a batch of 15. How many different samples are possible? All right, so if we're just randomly selecting 3 bulbs, how many different samples can we come up with? Well, the order of those light bulbs doesn't matter. We just want to know how many different ways are there of coming up with 3, taking 3 at a time. So this is going to be a combination. In a baseball conference with 8 teams, how many games must be played so that each team plays every other team exactly once? Here it doesn't say that the ordering of the games matter. It's just we want to make sure each team plays every other team once. So this would be a combination. All right, last one. In how many ways can 4 patients be assigned to 6 different hospital rooms so that each patient has a private room? All right, the rooms are different. So imagine the rooms being in a hallway. There are different rooms and a different ordering of those rooms. So we would say this is a permutation. All right, take a look at example 5. 5 cards are dealt from a standard 52 card deck. How many such hands have only face cards? Okay, so say you're dealt 5 cards and you're looking at your 5 cards and we want to come up with, well, how many different ways are there of coming up with a hand of 5 cards that are all face cards? So we're trying to figure out, okay, we have in our hand 5 cards that are face cards. How many ways could you have gotten 5 face cards? Well, in a standard deck of playing cards, we know that there are 12 face cards altogether. So because there are 12 face cards and you want to come up with how many ways can we have gotten 5 face cards, this would be 12 choose 5. It doesn't matter the order, so if you still have the same set of 5 cards but they're in a different order, we would call that the same hand. So 12 choose 5, which is equal to 12 factorial over 7 factorial 5 factorial, and simplifying that gives us 792. So there are 792 hands that are 5 cards that are only face cards. Okay, part B. How many such hands have a full house of aces and eights? So a full house of aces and eights means you have 3 aces and 2 eights. So we want to figure out how many different hands can we come up with that are 3 aces and 2 eights. So let's just write that down. We have 3 aces and 2 eights. Now there are 3 aces and we want to come up with how many ways are there of coming up with 3 aces out of the number of aces that we have, and how many ways are there of getting 2 eights out of the number of eights that we have. So this calls in the multiplication principle that we learned last time. Now we have to figure out how many ways are there of choosing 3 aces. Well, there are only 4 aces in a 52 card deck. So out of those 4, we choose 3. And then we also, for eights, only have 4 eights in a deck of cards. So we have 4 choose 3 number of ways to have 3 aces. And then we have 4 choose 2 ways of coming up with 2 eights. And then we multiply those, so that would end up being 4 times 6, which is equal to 24. So there are 24 hands that have a full house of aces and eights. Okay, how many such hands have exactly 2 hearts? So if you have exactly 2 hearts, that means you have 3 cards that are not hearts. So let's write that down first. So we have 2 hearts, and then 3 of anything else. Anytime it says exactly 2 hearts, that means that the rest cannot be hearts. Alright, so how many hearts do we have in a standard 52 card deck? Well, we have 13 of each suit. In this case, we have 13 hearts to choose from, and we only want to choose 2. So that would be 13, choose 2. Now we need 3 of anything else. How many cards are not hearts? That would be 39. So there are 39 cards that are not hearts, and we want to choose 3 of those. So this is 39, choose 3. Now we multiply those, and we end up with 78 times 9,139, and we get 712,842. So there are that many hands that will have exactly 2 hearts. Now you'll notice that there are only 78 ways of choosing 2 hearts out of the 13, but because the 3 can be anything else, that means there are 9,139 different ways of choosing the other 3, and so that's why the number gets so much larger when you multiply them together. Alright, last one. How many such hands have cards of a single suit? So in other words, in your hand, they're all either hearts or clubs or diamonds or spades, but they're all the same suit. So let's start off by picking a suit. It doesn't really matter which one. Let's say hearts. Let's say we're trying to figure out how many ways are there of coming up with a hand of 5 cards that are all hearts. Well, how many hearts are there in a standard deck of cards? There are 13, and we want to choose 5 of them. So 13 choose 5 is equal to 1,287. Now, because it doesn't say how many such hands have cards of just diamonds or just hearts, it's just a single suit. So it could be one of 4 suits. So since it can be any suit, we can take what we found for a single suit, 1,287, and multiply that by 4, because there are 4 suits in a deck of cards. So 4 times 1,287 is equal to 5,148. So there are 5,148 hands that are cards of just one single suit. So most of what we talked about today is the differences between permutations and combinations. How do we find combinations? And the important thing here is to be able to determine from a certain situation whether you're working with a permutation or a combination. Remember, permutations are where order matters, and combinations are where order does not matter.